So additive manufacturing, myself, Dr. Suman Das, Professor, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. Additive manufacturing, that is code PEME802F. Now, what is additive manufacturing? Additive manufacturing is the formalized term for what used to be called rapid prototyping and what is popularly called 3D printing. What is prototype? A prototype is an early sample, model, or release of a product built to test a concept or process. A prototype is generally used to evaluate a new design to enhance precision by system analysts and users. A prototype is the first or original sample of something that has been or will be copied or developed. It is the model or preliminary version. So this prototype is nothing but the preliminary version or the sample of the entire product. Now, rapid prototype, or this is called RP, rapid prototyping. The term rapid prototyping, that is RP, is used in a variety of industries to describe a process for rapidly creating. That means rapid prototype means nothing but the rapidly creating a system or past representation before final release or commercialization. That means before releasing the product, it is the first representation of the product. Now this is the evolution. So with the help of this slide, I will show the evolution of additive manufacturing. So first it was started, that is it came in the year of 1983, that is the SLA was invented first. After that 1986 patent of the SLA was filed, and that is 1988. After that 2000 and 2011, 13 and 14 and so on, that is and going on. Now distinction between AM and CNC machine. So what is the difference? So this is the conventional manufacturing, that is the subtractive manufacturing. First is the material, so after that with the help of machining, so the material, that is the 3D object, finally you are getting the 3D object, and this is the waste of the material. Okay, this is the figure A, and this is the figure B, that is the material, and after the additive manufacturing, that means the addition of the material, so finally we are getting the 3D product, and this is the waste of the material. So material waste is very minimum. Now what are the material used? So the polymetric materials, wax, paper, laminates. Subsequently there has been introducing of composite material, composite metals and ceramics. CNC CNC machine can be used for soft materials like medium density fiber board, that is FDF, machinable foams, and even some polymers are also used. When using CNC machining to make final products, it works particularly well for hard, relatively brittle material like steels and other metals alloys to produce high accuracy parts with well-defined properties. Now, what is the speed? So, high-speed CNC machine can generally remove material much faster than additive manufacturing machines can add a similar volume of material. Now the complexity. So higher the geometric complexity, the greater the additive manufacturing system. Now the accuracy. The additive manufacturing machines generally operate with a resol- uh, with resolution of a few tens of microns. The accuracy of CNC machine, on the other hand, is mainly determined by a similar positioning resolution along all three orthogonal axes and by the diameter of the rotary cutting tools. So this is the geometry. So AM, additive manufacturing machine, essentially break up a complex 3D problems into a series of simple 2D cross section with a nominal thickness. In CNC machining of surfaces must normally be generated in 3D space with sample geometrics like cylinders, cuboids, cones, etc. Now the additive manufacturing process chain. So this is the process chain. There are 1, 2, 3, 4, 5, 6, 7, and 8. So 8 process. First, number 1, that is the CAD model. From the CAD model, so the STL converter. Number 3, the file transformer to machine setup, build setup, remove, post processing, and application. So there are 5 steps. Now I will discuss these five. Sorry, there are 8 steps. So I will discuss that 8 steps one by one. 8 steps of additive manufacturing already I have mentioned. So these are the 8 steps. So the first one is the conceptualization and CAD. First of all, we have to produce a CAD model. So that CAD model have to be convert in the STL, standard triangulated line. Number 3, the transfer and manipulation of STL file into AM machine. So that file is to transfer into the AM machine. So next, the machine setup is required, and after that, that product will be built and part removal and cleanup. So after producing the product, so that will be removed from the machine setup and post processing. But this is there is any requirement of the removal of the sticky material or polishing is required, that is called post processing. That is the seventh operation. Finally, that is the application, that is the ready for the use. Now this is the step 1. So number 1, conceptualization and CAD. So first, the generic aim process start with the 3D CAD information. So first 3D CAD information is required. After that, there may be a many of ways as to how the 3D source data can be created. So 3D CAD model first we have to develop. The model description could be generated by a computer, and most 3D system are solid modeling system with some surface modeling components. So this is the step 1. First, we have to develop a CAD model. After that, so this is the summary of that. So all aim parts must start from a software model that fully describes the external geometry. This can involve the use of almost any professional CAD solid modeling software, but the output must be 3D solid or surface representation. So output of the CAD system, that must be 3D solid and surface representation. Now step 2. So step 2, that is the conversion to 3D. So that CAD model we have to convert into the STL. So STL is nothing but these stereolithography. So the term STL was derived from the stereolithography. STL is a simple way of describing a CAD model in terms of the geometry alone. It works by removing any construction data, modeling history, etc., and approximating the surface of the model with a series of triangular facts. So that means the converted into STL. That means that is standard triangulated line. That CAD model will be that we have to convert it into the STL method. The minimum size of these triangles can set within a most CAD software, and the object is to ensure the models created do not show any obvious triangles on the surface. And the process of converting STL is automatic within the most CAD system. That means this process is automatically converted. So in the CAD, in the process, that is the STL, standard triangulated line. So total CAD system, that means the total CAD will be converted into STL method. So STL files repair software is used when there is a problem with the file generated by the CAD system that may prevent the part from being built correctly. The complex geometries, it may be difficult to detect such problem while inspecting CAD or the subsequently represented STL data. So STL, standard triangulated line, is essentially a surface description. The corresponding triangles in the file must be pointing the correct direction, so that each and every STL, that means standard triangulated lines, must represent the entire surface. While most error can be detected and rectified automatically, if any error is detected, that can be rectified automatically. Now the summary. Nearly every AM machine accepts the STL file format. Okay, and nowadays nearly every CAD system can output such a file format. This file describes the external closed surface of the original CAD model and forms the basic of the calculation of the charts. Now step number 3. Transfer to AM machine and STL file manipulation. So that step 3 is the to transfer that into the AM machine. Once the STL file has been created, it can be sent directly to the target AM machine. So after creation of that STL file can be directly transferred to AM machine. It should be possible to press a print button and machine should build. There may be a number of action required prior to building the part. The first track would be variety, that is that the part is correct. The user may wish to reposition the part or every change the orientation to allow it to be built at a specific location within the machine. And it is quite common to build more than one part in an AM machine at a time. So with the help of AM machine, so more than one part can be built at a time, and this may be multiple of the same part, a copy of the machine, or different STL file. Now this is the summary of this step 3. The STL file describing the part must be transferred to a AM machine. Here there may be some general manipulation of the file so that it is the correct size, position, and orientation of the building. Now machine setup. So all AM machine will have at least some setup parameters that are specific to the machine to machine or process. So every machine having some particular setup process. Some machines are only designed to run perhaps one or two different materials and with no variation in layer thickness or other building parameters. So few machines are only set up particularly for one or two materials. So there is no variation. That's why it is written here. In the more complex cases, to have difficult setting or save files for previously defined setup to help speed up of the machine setup process and prevent mistakes. So this is the summary of this four. The AM machine must be properly set up prior to the build process. Such setting would relate to the build parameters like the material constraint, energy sources, layer thickness, and timing. That means every machine setup having a particularly specification, particularly parameters. So what type of machine setups are required? So that is varying from machine to machine. Next, step 5. So that is the build up. Build setup. The first few stages of AM process are semi-automated tasks that may require considerable manual control, interaction, and decision making. Once these setups are completed, the process switch to the computer controlled building phase. All AM machines will have a similar sequence of layer control using a height adjustable platform, material deposition, and layer cross section formation. That means every machine having a adjustable of their height as per the requirement of the product deposition of the product. And all machine will repeat the process until the build or complete or there is no source material remaining. So the process will be not be finished, so until the entire process is going. So all process will be repeated. The process enter either the build or the process, there is no source material remaining, no source material remaining until the process will be continued. So this is the summary of the step 5. Building the part is mainly an automated process, okay, and the machine can largely carry or without supervision. Only superficial monitoring of the machine need to take place at this time to ensure no errors have taken place, like running out of the material, power or software glitches, etc. So automatically the process will be going on. So there is no extra supervision, there is no extra care is required. So no extra supervision is required. Only some monitoring is needed. Now that is step 6. So removal and cleanup. So these are the steps. So the output from the AM machine should be ready for use. So after creation of the die, that is ready. More often, the parts still require a significant amount of manual finishing before they are ready for use. Some manual finishings are required before going for the final dispatch for ready for the use. The part must be either separated from the build platform on which the part was produced or removed from the excess build material surrounding the part. So excess build material should be removed from that part. So and the part is ready. So this is the summary. Once the AM machine has completed the build, the part must be removed. So that part must be removed from the build setup. This may require the interaction with the machines which may have safely interlocked and ensure the example that the operating temperature are sufficiently low or that there are no actively moving parts. So post process. So what is post process? Post process refers to the usually manually it is done by manually stages of finishing the parts for application purpose. So this may involve abrasive finishing, that means with the help of abrasive material. So like polishing, surface should be removed, should be polished, and sandpapering or application of coating. So there is some coating or painting is required for better surface finish, better look. Summary of the step 7. Once removed from the machine, part may be required an amount of additional cleaning up before they are ready for use. This therefore often requires time and careful, experienced manual manipulation. So this is the step 7. Some extra care, some extra surface finish, some painting, mm, something is additionally required for improving the surface texture. Step 8. Although part may be made from the similar materials to those available from other manufacturing process like modeling, molding and casting, parts may not behave according to the standard material application. Some AM process create parts with small voids or bubbles trapped inside them, which could be the source for parts failure under mechanical stress. So this is the summary of step 8. So parts may now be ready to be used. So this is the last step. However, they may also require additional treatment before they are acceptable for use. Example, they may require priming and painting to give an acceptable surface texture and finish. So for better surface texture or better finish, some painting also required. They may also be required to be assembled together with other mechanical or electronics component form final model or product. So this is a part. So with the help from the other parts are required for assembling. So they may also be required for assembling together with other mechanical or electronic components. Okay. So this is the summary of the step 8, the final one. Now, thank you.